Greetings and welcome to the problem set number 1 overview for Chemistry 151. Problem set number 1 is the first of several problem sets we'll look at this quarter. Chapter 1 introduces kind of the base pieces that you need for chemistry. So it'll talk about conversions, metric units, how to do some simple kind of things in chemistry, stuff like that. This video was created as a way to get you unstuck if you are working on the problem set and you just get stuck on a problem. This video is not meant to go through and essentially copy the problems down. However, what I would do to get the most out of this is I would try the problems from the problem set first on your own. All right, see if you can do them. And then for the ones you get stuck, you can kind of scrub through this video. You don't have to watch it like minute by minute, but you can actually move the little slider around to get to the problem you want to. And you can look at my explanation as to how it's done, and then hopefully that will help you get through it so that when you're ready to turn in the problem set, you are good to go. So definitely feel free to move around this video. You don't have to listen to all of my silly jokes and horrible references. That's for sure. On the other hand, if you really are getting stuck, then yeah, that's what this is there for. If you do have further questions outside of this video, you're welcome to contact me. Email is definitely the best way, mike.russell@mhcc.edu. You can also talk to the LSC Avid Center at Mount Hood Community College. Their website is mhcc.edu/LSC, and they have tutors that can meet with you both in person and online. I highly recommend that you check them out. So without further ado, let's look at problem set number 1. Let's start going through the problems. Again, feel free to stop this problem, pause it, rewind it, forward it, whatever you need to as you go through it. But this first question is just finding the number of significant figures in each of these numbers. And you can see that all these numbers have a lot of zeros in them. The zeros are what make significant figures kind of crazy. Most of the time, the zeros that start a number are not significant. So for example, in question A, that 0 is not going to mean anything. That's not going to be a significant number. These zeros right here in the second one, those also will not be significant. They're just telling you where that 7 starts on the number line, all right? So zeros to the left of the non-zero are like next to the left of 7 or 1 are usually not significant. And these zeros right here also fall in that category, all right? So we can cross out all of those numbers right away. Now, if the 0 is after a non-zero number and it's to the right of the decimal, it counts. So this 0 is significant. It actually is a number that's meaningful. Chemists wouldn't write that number unless there was a reason for it. And also numbers, zeros that are between non-zeros also count. So all of those numbers are significant. Let's go to the last one there for a second. These zeros right here are significant because they're between non-zeros, no problem. However, zeros at the end of a number, yet before the decimal, those are the ones that are hard to say. In Chem 151, we would say that these zeros in F don't count. They're not significant. They're just part of the placeholders telling you where you are on the number line. Now on C and D, the difference between them is D has a dot and C does not. In C, all of those zeros would be considered placeholders. All right, they don't count. They're not significant. Only the 4 on that one would be significant. But if there's a dot, that means that those zeros count. They are significant. I want to stress the importance of those numbers. 4,000 without a dot would be like plus or minus 1,000. So 4,000 without a dot, you could have somewhere between 3,000 and 5,000, a pretty good uncertainty. 4,000 with a dot, the plus or minus would be at the 1 spot. So 4,000 with the dot would be 3,999 to 4,001, a much smaller plus or minus. And in this experimental field, that's important. So the first one, to go back to it, 7 significant figures, 1, 1, 1, 1, 0, 1, 0, all of those significant figures, but the first 0, like we talked about, is not significant. The second one has only 1 sig fig. All of those zeros are just placeholders. We could call that, as in scientific notation, we would call it 7 times 10 to the minus something, all right? And that would be a legit way to say it. So all those zeros are not meaningful. 4,000 without a dot at the end is just a 1 sig fig number. Usually zeros past a non-zero but before the decimal are not significant unless on the next one they do have a dot. Then those zeros all count. So 4,000 with a dot in scientific notation would be 4.000 times 10 to the third. We would include all of those zeros. But the next one, only the last 4 and 0 are counting. 4.0 times 10 to the minus 3. And for the last one, the last 2 zeros don't count, but all the other ones do. 6 significant figures. We're going to round these numbers to the designated number of significant figures. And remember, if the first number you drop is between 5 and 9, then you round up. But if the first number you drop is between 0 and 4, then you don't round up. So in the first one, 3883, and we're going to round to 2 sig figs, we'll cut it off after the first 8. So what that means is that the first digit dropped is an 8. That's between 5 and 9. We would round that up. It would be 3,900. 3,900 would be a 2 sig fig version. So we did round the 8 to the 9 because the first digit dropped between 5 and 9. Now the next number, we're going to cut it off at 2. The 3 and the 0 would be the 2 sig figs that we would keep. The initial zeros, remember, are all placeholders. So the first digit dropped is a 1. That's between 0 and 4. That means we don't touch it. We're going to leave that one as it is. I'm going to write it in scientific notation because I hate counting zeros. 3.0 times 10 to the minus 5. You could also call that 0.000030, but I certainly recommend that you write it in scientific notation, make it easier on your instructor. The next one, 3 sig figs, 4.40, those are the first 3 sig figs. We'll cut it off after that. First number is between 5 and 9, so we'll round up, 4.41. The next number, 2.10, we're going to cut it off at 3 sig figs. Cut it off right there. 0 is between 0 and 4, so it's just 2.10. All right, pretty chill. Remember to round up. It's easy to forget that, but it is an important part of these problems. In this problem, you're going to have some experience applying significant figures and also using your calculator. So the first part of these kind of problems is just to throw the things in your calculator and see the answer you get. However, remember that in the significant figure world, you usually don't want to include all the answers that the calculator gives you. So when you multiply 3.33 times 3.03 times 0.0333, you're going to get some crazy number. But the punchline, you want to have only 3 sig figs in your answer. So when you solve this, it comes out in your calculator, 0.33599,367. How many sig figs to use? That's going to depend then on the number of sig figs. And you can see that 3.33 and 3.03 and 0.0333, they're all 3 sig fig numbers. So we're going to cut this number off after the 5. The first number that's dropped between 5 and 9, definitely. So 0.335 becomes 0.336 for the final answer. Oh joy. The next one, if you throw it in your calculator, it comes out to be this crazy thing. 8.00 blah 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 times 10 to the 9th. But wait, 1 sig fig, and that's because 20,000 doesn't have a dot. Now that's a huge number, but it only has 1 significant figure. So the final answer is only going to have 1 significant figure as well. Remember, when you multiply and divide, the smaller number of sig figs goes through. So since 20,000 has only 1 sig fig, our final answer, only 1 significant figure as well, 8 times 10 to the 9th. Now, on the next one, we have a combination of adding and dividing, all right? So you've got to be really careful here and then think about what's happening. In your calculator, I hope you can all get this, 0.6366565696, etc., etc. But notice here how we're rounding up to 3 sig figs. And this can be a little confusing at first, but it all has to do with the doubtful digit. So for example, on the bottom part there, you've got 3.200 and 6.73, and you add these together and you get 9.930. But remember, when you add and subtract, you cut it off at the largest doubtful digit. So this part right here comes out to be a 3 sig fig number, all right? You'd want to use the whole number on the bottom, but it really is only a 3 sig fig number. And the same thing's going to happen right here. You're going to be left with 6.322 on the top, but you want to cut it off at 3 sig figs, the hundredths place, because of the 4.00. So it's essentially like having 3 sig figs divided by 3 sig figs. That's why this number is only 3 sig figs as well, 0.637. So watch the adding and subtracting. You want to use all the numbers in the calculation, but it is a good idea to go back and figure out how many significant figures you've got. The next one, we have multiplying and dividing. 4 sig figs divided by 4 sig figs and 4 sig figs kind of sets that out at 4 sig figs, 0.4598. First number there to be dropped is a 1, so no problem. And then the last one, 5,600 times 300 divided by 22 divided by 97.1. If you look carefully at those numbers, 300 is just like our 20,000 earlier. It's a 1 sig fig number. So the final answer here would be 8 times 10 to the second, or 800 without a dot. The number 786.4 or whatever, you want to cut it off after the first sig fig. 8 is between 5 and 9, round up, 800. Oh joy. In this problem, we're going to add and subtract some numbers, and we're going to cut it off at the correct number of sig figs. And on these, you want to look for the largest doubtful digit. That's going to determine where your number starts or stops. So for example, on the first one, all of these numbers, the 7s, they all stop at the 1 spot. So whatever your answer is, you have to stop at the 1 spot as well. So throw this in your calculator. I had exactly 281. 281 stops at the 1 spot, so the final answer 281. And notice how we went from a 1, a 2, and a 3 sig fig number, and we ended up with 3 sig figs. That does happen when you add and subtract. Sometimes you end up with more sig figs, sometimes you add up with less sig figs. Kind of strange. The next one, if you look at those 3 numbers, the 3.1 numbers, it's the last one, which is the important one, because that one stops at the tenths. That's the largest doubtful digit. So whatever the answer is, you have to stop it at the tenths as well. 9.321 is what the calculator told me, but we're going to cut it off at 9.3. 3 is the tenths spot. That's where the 3.1 stops. That's our largest doubtful digit. 2 is the first number to be dropped. It's between 0 and 4, so we don't have to do anything to the 3. Now on the next one, another addition problem, notice the 37. 37 stops at the 1s spot. So whatever our answer is, we have to stop it at the 1 spot as well. 235.45 goes to the hundredths, 36.4 goes to the tenths, but it's 37 that stops at the 1 spot. That's going to mess us up. So the answer, 308.85, cut it off at the 1s, which is the 0.85. 8 is the first number to be dropped, so we'll take the 308 and round it up to a 309. Good to go. The next one is subtraction, but again, same idea. We want to see where we're going to cut it off. 4.72 stops at the hundredths, and the 8 here is at the thousandths. So the answer here, we're going to have 2 spots to the right of the decimal, and that's where we're going to cut it off. So mathematically, 0.812, but we have to cut it off at the hundredths, so that would be 0.81. Notice here how in this problem, we went from a 3 sig fig 4.72 and a 4 sig fig 3.908 and turned it into a 2 sig fig number, 0.81. Again, this also happens when you add and subtract. The last number, we've got the huge 46,230 number added to 325 plus 45. It might be tempting to say, oh, we'll cut it off at the one spot. But remember, in my world, if you have a 0 that doesn't have a dot before the decimal point, that 0 doesn't count. So 46,230 stops at the tens spot. So this answer in your calculator comes out to be 46,600, all right? You don't want to include all those zeros. You do want the first 0 because the 10 spot stops right cut it off, but you get the idea. Let's see if I can erase a little bit. This thing is weird. There we go. You can see there that this first 0 is meaningful, the second 0 is not. And since the second 0 is the first one dropped, is it between 5 and 9? No. So we'll leave it as is. 4.660 times 10 to the 4th is how I would write it. That shows that you have a number which has 4 sig figs. It stops at the 10 spot. Scientific notation can be a good way to do these problems. Let's express these numbers in scientific notation. Now, you can do this old school and write it times 10 to the 0 and then change the exponent depending on if you go right or left. So, for example, in the first one, you'd end up moving the decimal to the left so the number gets bigger in the exponent, and the other one, and the second one, it would be the opposite. However, I'd like to encourage you to really get to learn your calculator, because I'm sure that your calculator has a way to go from scientific notation back to regular and regular to scientific notation. And that's the way to go on these problems. If you can do that, it makes your life so much easier in chemistry. So take this as a call. Pause the video. See if you can figure it out. All right. Now, assuming you have figured it out, then you just want to figure these out. Remember that numbers larger than 1 will have positive exponents in the times 10 part. So this would be 7.876 times 10 to the 2nd. Again, if you move the decimal to the left, you end up making a positive exponent. So we moved it 2 to the left. That's where the positive 2 comes from right there. Now, the next one is a number less than 1. We're going to move this 1 and 2 to the right. So it's going to be 1.798 times 10 to the negative 2. If you move to the right, it becomes negative. So this would be 1.798 times 10 to the negative 2. Remember, powers of 10 that are larger than 1 are big numbers, and powers of 10 that are less than 1 are numbers less than 1. The next one would be 4.00 times 10 to the 1st, and the last one, 6.75 times 10 to the 5th. Now, notice on these two, the first one, I included all the zeros because those are significant zeros, but the last one there, we blocked the last 3 zeros because they were just placeholders. There was no dot at the end of those zeros, so the zeros were just telling us where they were on the number line. So only the sig figs end up in the scientific notation part, which is kind of neat. All of these numbers are associated with a metric prefix, or the metric prefix is associated with a number, so tell what it is. And these are the 5 metric prefixes we're going to use a lot, so that's why they're there. 10 to the minus 3 is the milli. It's used a lot for milligrams, milliliters. If you drink things at the store, a lot of times pops and sodas will have milliliters on them. But 10 to the minus 3 is for more than just volume. It can also be for grams. You can have a milligram or a millimeter if you're doing mass or length, respectively. So 10 to the minus 3 is milli, which is the little m. 10 to the minus 9 is nano. That's one we'll use a lot when we're talking about light, and light can be really helpful in chemistry. Nano gets the symbol N. 10 to the 3rd, one of the bigger ones, is kilo. A kilogram is 10 to the 3rd grams, or a kilometer is 10 to the 3rd meters. Micro, which is used a lot in biology more than chemistry, but sometimes chemistry too. Micro is 10 to the minus 6. Micro gets that cool Greek symbol, this mu, it looks something like that. If you see it, now you'll know what it is. And finally, centa is centimeters, centigrams, stuff like that. Centa is 10 to the minus 2. So all of these 5 are going to be really handy, and it's nice to know those 5. The other ones, deci and mega and those kind of things, are nice to know, but they're not as important as these 5. In this problem, we're going to calculate the volume of these different things. And volume is just amount of three-dimensional space, basically it takes up. Different objects have different equations for them. In the back of your mind, though, keep remembering that this is probably also going to be a problem about significant figures. So we've got a cube on the first one. Volume equals side cubed or edge cubed. So in this first one, there's the edge, that number. We'll take it to the third power. On your calculator, you have either the x to the third button that you've got it, or you can use that little caret. It looks like an arrow. The caret on a calculator looks like that. You can go caret 3. But either way, make sure you know how to do this, because once in a blue moon, we'll do this kind of stuff. On the first one, the number in the calculator, 43.521346, etc., we want to cut this off at 5 sig figs. Raising to a power is like multiplying and dividing, so sig figs in equals sig figs out. 5 sig figs, 43.521 millimeters cubed. And notice there that because we had millimeters, we ended up with millimeters cubed. The next one is for a sphere. All right, the sphere has a radius r of 1.212 centimeters, and you can see there's the equation 4/3 pi r cubed. So for the next one, plug those in. Pi is a number probably in your calculator, 3.1416. Your calculator will give you a better value. 4/3, of course, just that, and then take in the radius to the third power. There's what you get in the calculator, but again, you want to cut it off to 4 sig figs because 1.212 is 4 sig figs. Pi is like unlimited sig figs for us. I mean, it just goes on and on and on and on and on, which is cool. And 4/3 is an exact conversion. It's always going to be 4/3 in the volume of a sphere. The next one is a bar, not those kind of bar. If you're 21 and over, if you're under 21 or 19 in Canada, then anyway, I'm digressing. A bar here is a three-dimensional object, length times width times height, and you've got all the ones, and they're all in meters, so we don't have to convert anything. Throw it in your calculator, length times width times height, 2 sig figs, 0.12. And because all of those were in meters, the volume will be meters cubed. All right, pretty chill, 0.12 meters cubed. And then the last one, we've got a cylinder. This happens a lot with wire and stuff like that. Anyway, volume equals pi r squared L. So we've got a length in millimeters, we've got a radius in millimeters. Everything is the same kind of millimeters. There's our good friend pi again. We'll plug all of those things in. You get a number with a lot of digits, but we can only use 2 of them. 3.2 and 62 are both 2 sig fig numbers. So we'll cut it off 1994.53, whatever. Cut it off at 2 sig figs. First digit to be pulled between 5 and 9. So that becomes 2.0 times 10 to the third. That's the way I would write that number to reflect 2 sig figs, etc., etc. Got a piece of metal, 187.6 grams, and it's placed in a graduated cylinder, which is a way to figure out volumes of liquids. The cylinder has 225.2 milliliters, and after adding the metal, it goes up to 250.3 milliliters. We want to know what the volume is in centimeters cubed, and then finally the density of the metal. Now, I'm messing with your units here a little bit. You can see that we had milliliters of water and then milliliters of water plus metal. And I want you to find the volume in centimeters cubed. And that might be daunting, except 1 centimeter cubed is equal to 1 milliliter. That's one of the definitions. So you could replace milliliters with centimeters cubed and centimeters cubed with milliliters. No problem, go back and forth. So the first part, to find the volume is additive. So 250.3 minus 225.2, that's going to give you the volume of the metal. It's literally a displacement. 25.1 centimeters cubed, which is the same as 25.1 milliliters, that's the volume. And then the density, the next part, you would just take the mass that was given, divided by this new volume, and notice here I flipped it over to milliliters, just trying to make it more fun. Anyway, the number that comes out in the calculator is crazy, but we can use 3 sig figs because of the volume, 7.47. And again, this is adding and subtracting. We're going to cut it off at the tenths. So cutting it off there, 25.1, that's where the 3 sig figs come that we're using in our final answer of 7.47. This is called the displacement method. It's super handy for solids. Solids don't usually have, or have usually very rigid sides and corners, so it's hard to do them, but displacement in a liquid makes it pretty easy. We got a dose of a chemical in a pediatric clinic for kids, and we'll say that it's 225 milligrams of this drug per kilogram of body weight. And we want to know how many milligrams of this stuff we need to add to a child who weighs 12.3 kilograms. And this question is kind of important to me. When I was, a few years ago, my son, and I was kind of a paranoid parent, I admit it, but anyway, we brought him into the hospital. We thought he was dehydrated, and he wasn't. It's a long, silly story that's kind of embarrassing now, but the reason I bring this up, I was really tired, I was a little frazzled, and the person helping us, the nurse or whoever, man, they could not figure out this kind of a problem, and it was just driving me crazy because I was already on edge a little bit and stuff like that, and this person couldn't convert the dosage over for anything. So anyway, it became my reason for living, if you will, that I wanted to make sure that everybody that goes through my classes knows how to do this kind of problem. And this is classic dimensional analysis. We've got a unit, 12.3 kilograms. We want to know how many milligrams of the drug we need to go through. So the starting unit, 12.3 kilograms, and this part, 225 milligrams per kilogram, that's our conversion to go from kilograms to the milligrams. And it's not a hard problem, all right? It really isn't. And I don't know why that person couldn't do it that day, but that's a long story. So anyway, starting 12.3 kilograms, 225 milligrams of the drug given per kilogram of body weight. So notice how a kilogram on the top cancels the kilogram on the bottom. That's the whole idea behind dimensional analysis. The old unit is gone. The new unit, milligrams of the drug, are left over. In the calculator, you get this number, but we can only use 3 sig figs. 225 is 3 sig figs, and 12.3 is 3 sig figs. So instead of 2767.5, we'll cut it off after the 6, the first 3 sig figs. 7 is between 5 and 9. 2770 milligrams. And you could write that 2.770 times 10 to the third. That would be fantastic too. But that 0 is not a significant figure, not a significant number. So 3 sig figs, you can now convert over drugs and stuff if you need to in a medical experience. And my work is done here. Well, at least for today. Anyway. We've got a 2004 penny from the United States. It's zinc plated with a thin layer of copper. The mass of the whole penny, 2.552 grams, and we find that it has 2.448 grams of zinc. So there's not a lot of copper in it, but a little bit, all right? We want to know the mass percentage of the copper and the mass percentage of the zinc. Okay, if you see a problem like this with a mass percentage, it's always total sample mass on the bottom and mass of what I call the good stuff on the top. So for example, on the zinc, if we wanted to find percent of zinc first, 2.448 grams of pure zinc on the top divided by total mass, 2.552 on the bottom, times 100%. That's all a mass percentage is. Now the mass percentage of copper, we'd have to first figure out the difference between 2.552 and 2.448. We want to find the grams of just copper, but we'd still divide it by 2.552 grams times 100%. So this is super common in chemistry. It happens all the time. All right, so here's the percent copper calculation. First thing, you got to figure out how many grams of copper you've got. So total minus zinc, in this case, is going to give you grams of copper, 0.104. So percent copper, grams of copper divided by total penny times 100%, 4.08% copper. You bet these things are susceptible to sig figs. Both the numbers we started with stopped at the tenths under the thousandths. So this number stops at the thousandths. It's a 3 sig fig number. So the percentage down here in decimal form, 0.04075, blah, blah, blah. Cut it off at the third sig fig. That's the 7. This number, the first number to be dropped, is between 5 and 9, so you raise the 7 to the 8. And again, if you multiply by 100%, 4.08% copper. Percent zinc is even easier. We've already got the numbers for that. 2.448 divided by 2.552 grams of zinc divided by grams of everything times 100%, 95.92% zinc. All right. And again, cutting it off at 4 sig figs this time because both of the numbers we have here are 4 sig figs. So 0.9592 is what you'd get before you multiply by 100%. The 4 is the first thing to be dropped. Don't have to raise anything. You're good to go. Now, if you've done these problems right, if there's only 2 components, they should add up to about 100%. And you can see in this case, definitely 95.92 plus 4.08, that's 100%. It will be very, very, very close to 100%, probably 100%. If it's not, it could be a sig fig thing, I'll be honest. But more often than not, they should round up to 100% if there's only 2 components. And that's a cool thing to remember in the back of your head. Here's some problems with temperature, all right? Now, most of the time in chemistry, we're going to use Celsius in the lab, which we have thermometers for. A lot of times for calculations, we'll use Kelvin. We'll see Kelvin's really handy. But we live in the United States of America, where all the radio and TV stations continue to use Fahrenheit. So it's a good idea to know how to go from Celsius to Fahrenheit or Fahrenheit to Celsius. It's cool to make connections with the real world and what we're learning here. So this first question, before we go there, Kelvin equals Celsius plus 273.15. So that's the equation we're going to use a lot, and that's a good thing to know / memorize. Kelvin temperatures cannot be, for S anyway, cannot be negative numbers. All right, so if you get a negative Kelvin, you have probably done it wrong. Celsius temperatures can be negative though, and that's a cool thing to remember. So this first question, 234.3 Kelvin, we want to turn it into Celsius. So 234.3 equals X, our unknown Celsius, plus 273.15. To figure out X, we would go 234.3 minus 273.15. And if you do that, you get negative 38.9 degrees Celsius. Now, notice that I used 273.15. So the answer that came out of the calculator was this one right here. But this is where adding and subtracting the sig fig rule is so important. The number we were given only went to the 10th. So this number here has to only go to the 10th as well. 5 is between 5 and 9, so round up, negative 38.9 degrees Celsius. The second question, this chickadee is 41 degrees Celsius, 41.0. What's the temperature in Kelvin? Okay, no problem. So we'll add 273.15 to it. Like with the last one, because 41.0 only goes to the 10th, our final answer will only be to the 10th. So even though the number gives 313.15, we're going to round that up. 313.2 Kelvin would be the answer. This last one is a problem where we've got Celsius and you want to find Fahrenheit. This is the equation right here that you're going to use. All right, Fahrenheit equals 1.8 times the Celsius temperature plus 32. So in this case, T of Celsius is 60. We'll multiply that by 1.8 and add 32. 32 is considered an exact number, so it doesn't affect your sig figs. Think of it as 32.0000000, etc., etc. Anyway, when you do that particular one, Fahrenheit equals 9/5 or 1.8 times 60 plus 32, 140 degrees Fahrenheit. And that number there, we're putting a dot by it because we do want to keep it to the one spot, just like this one is right here. Notice 1.8 and 9/5. This is another joyous thing about Fahrenheit. 9/5 is 1.8, and there's reasons for writing them both like this. You'll see them both ways. Just realize 9/5, 1.8, same thing. Pretty chill. Again, in this class, Chem 151, and in the 200 level, we're going to focus more on Celsius and Kelvin going back and forth. Not as much with Fahrenheit, but it's a good idea to know how it works. This question, we've got a whole bunch of different measuring tools, and we want to know the level of uncertainty in each device, okay? And the punchline of this one is that you always record to one more decimal point than you have the markings for. So let's see how this works. In the first one, we've got a graduated cylinder with 10 milliliter intervals. So that means on our graduated cylinder, there are lines for 10, 20, 30, 40, that kind of thing. Well, we could probably guesstimate if it was 15 or 20 or 25, all right? If it's going to be the doubtful digit, some of you might get crazy and go like 14, 16, cool, no problem, it's the doubtful digit. But the thing is if the lines go to every 10 milliliters, we can guesstimate to the 1 milliliter. We're going down a power of 10. So on this first one, we would say plus or minus 1. 10 is the 10 spot, down one more would be the 1 spot. So we could guesstimate that. You wouldn't want to go like 10.0 or something like that. That would be too many guesstimates. But 10 or 15, we could do that and stuff, no problem. We could see between the 10 milliliter intervals what was happening. Now on the next one, the meter stick has 1 centimeter intervals. So that means 1 centimeter, 2 centimeters, 3 centimeters. So we could probably guess like 1.5 or 2.0 or 2.5. We could guess to plus or minus 0.1 centimeters. So notice we're just going down one level, one more than the lines are. And that's the punchline of this one. So this next one, Biuret, which is something we'll use in lab in the 200 series, it has 0.1 milliliters. So 30.1, 30.2. That means you could guesstimate 30.15 versus 32.0, something like that. We can go to 0.01 milliliters. So all your measurements should be 0.01. On the other hand, if you've got a scale that only goes in 100 readings, one of these old school pan balance scales, then that means you could guesstimate to 1 less power of 10. That would be plus or minus 10, all right? So you could guesstimate 150 versus 200 or something like that. And again, that doubtful digit may be kind of far off, but at least it gives you an idea what it's supposed to be. That's the important part. We've got 3 students recording the same object. And if you use a super high-powered device, the actual quote-unquote measurement, 13.452. And we'd like to look at those 3 students and say, how are they in regards to accuracy and how are they in regards to precision? Now, accuracy is the easiest one because we know that the value is supposed to be 13.452. And student B did a really good job on their measurements, and all of their measurements, 13.4, 13.5, right around 13.452. So student B, we would say, is very accurate. Their measurements were really close to the known value for this number, all right? Student C didn't have a clue, let's be honest. They're not even close to 13.452. They're all a lot bigger. So I don't know what was happening with student C, but student C didn't do a very good job in terms of accuracy. The numbers aren't very good. A didn't do a very good job either. Now, if you averaged those 4 numbers for student A, it would come out to be about 13.6-ish, which isn't too bad. I mean, it's not too far away from 13.452. I hesitantly say they're okay for accuracy, but if you want to say they're not good for accuracy, that's totally fine too. But the other part that a chemist has to think about is precision. And that's how close your measurements are to each other. And let's go back to stellar student B, because student B, all of the numbers were really close to each other. They had a small plus or minus from each other. So 0.4, 0.5, 0.5, 0.4, they're all within 0.1, very, very close to each other. Student B, accurate and precise. Accurate because their measurements were close to the actual 13.452 number, and precise because they're all pretty close to each other. There's not a very big plus or minus. Now, student A maybe was okay for accuracy, but their precision wasn't very good. Like you can see, it went from a low of 0.3 to a high of 0.9. So that's a pretty big plus or minus right there. So I wouldn't say that student A was very precise. I mean, maybe accuracy, maybe, but precision, not really. Now, student C, for all else I said about them earlier, student C's answers, they look like they're pretty precise. Like 14.0 is the median, 2 were a little less, 1 was a little bit more, but a much smaller deviation of the numbers from each other. So I would say that student C was precise, even if they weren't very accurate. So again, to kind of summarize here, student A, not really any precision at all. The numbers were plus or minus quite far from each other. Low accuracy, maybe some, all right? I don't know, the average was kind of close. I don't know, I'm not liking that the more I think about it. Not very good accuracy, let's put it that way. Now, student B, on the other hand, high precision, all the numbers very close to each other, and also high accuracy. They were close to the actual number. Student B did a great job. Student B is what we strive for, right? On the other hand, student C, accuracy was way out there, really bad, not even close to 13.45, but their precision was really high. The numbers were all really close to each other. Now, a lot of times in chemistry, when you don't know what the actual number is, if your numbers are close to each other, that of course means then you have high precision, and you should pat yourself on the back for at least being able to repeat an experiment with some reproducibility, like you're doing a good job. Often, high precision means high accuracy, but that's not always the case. Student C had high precision, so whatever they were doing a consistently good job at. Unfortunately, though, the accuracy just wasn't there. So you've got to take these kind of things into account when you're a chemist. Here's some students. They were looking at the boiling point of this benzaldehyde. And normally benzaldehyde boils at 178 degrees Celsius. And student 1 was 175, student 2 was 190, and student 3 was 181. We want to find the percent air associated with each of these students' boiling points. And there's the formula for percent air. Now let's look at this formula real fast. Absolute value means if there's a negative number, make it positive. All right, that's all it means. And you're taking the absolute value of the difference between the actual number, 178, and the experimental numbers, those three numbers right there. So you can see that like 178 minus 175 would be positive, but 178 minus 181 would be negative. Whatever order you do it, turn the negatives into positives. That's what absolute value is. And we're going to divide it by the accepted value, which is 178 times 100%. So all of these numbers are going to be positive numbers. They're all going to be positive percent errors. So now it's time to just plug and chug. So student 1, 175 minus 178. Initially, that comes out to be a negative number. We're going to divide it by the accepted 178 times 100%. Before we do absolute value, it's negative, but with that absolute value, we'll do positive. Technically, this is a 1 sig fig number because of this part right here, 2% error. All right, so they were pretty close to the actual value. Student 2, 190 minus 178 would be the difference, divided again by 178 times 100. Technically, because 190 minus 178 is 2 sig figs, 6.7%, a little bit more error in the student 2's measurement than number 1, which kind of makes sense if you look at it. And then student 3 also had a 2% error when you count for absolute value and all that kind of stuff. So this is another way that scientists use to tell how close measurements are to the actual values, and this is the kind of stuff we'll do throughout these classes. Here's some different phenomena, and I'd like you to tell me if it's a physical or a chemical property, all right? Physical properties are reversible, and chemical properties would be very difficult to go back to the original form. All right, so the first one, we've got powdered beryllium that's burning. All right, first of all, anytime you've seen something burn, it's very difficult, if not impossible, to get it back to the original thing. So that first one is absolutely a chemical property, all right? It burns well, that's cool, but it's going to be hard to get your beryllium ash or whatever back to the original beryllium chemical property. The next one, the metal melts at 1287 degrees Celsius, which is pretty high. If we wanted to take, though, the liquid beryllium and get it back to the solid, we could do that, all right? So melting, boiling, stuff like that, if you're careful, those are reversible. I would call that a physical property, all right, something we can get back. The density of beryllium, 1.85 grams per centimeter cubed. Well, we can make that measurement and we still have the same beryllium. We haven't made it irreversibly ash or something. That's going to be a physical property. And if we notice that the beryllium is relatively soft and a white metal, all right, well, we haven't turned it into an oxide or something like that. That's going to be physical as well, all right? So physical things are reversible. It's usually melting points, boiling points, density, stuff like that. Chemical things are going to be hard to go back. So if it makes a compound or something like that, or if it burns, those would be hard things to do. Reacts with acid. Mixtures and pure substances are really important. A heterogeneous mixture is when you have two or more pieces, but you can see that they're different. So like rocks in water. That would be heterogeneous. The rock solid, the water liquid, but you know you've got a mixture. That would be a mixture. Homogeneous mixtures, you can't always tell. So for example, salt water and water both look the same, looks like a clear liquid. Homogeneous mixtures mean you have only one phase. So salt water would be a homogeneous mixture. It all looks the same. Sugar water would be the same, etc., etc. Pure substance would be the water itself, all right? And so you only have one species inside there. Now, the composition can be constant only in the pure substance. Heterogeneous mixtures, homogeneous mixtures, a lot of times you'll have things like settling down, the more dense things on the bottom, the less dense things at the top, or there'll be thermal kind of heat things and stuff like that. But water, you can heat it up, cool it down, whatever, but it's still going to be just water. So the only one with constant composition will be the pure substance. By the way, pure substances will be compounds or elements, by the way. I've been talking about water, a compound, but it could be an element. Which one can you separate into simpler substances by physical means? That's going to be the mixtures, all right? So you could literally take the rocks out of the water in the heterogeneous mixture we talked about earlier. For homogeneous mixtures, you might have to boil the liquid. So you could boil the salt water. The water would go to one place, which could be collected, and the salt would be in another. But those are all physical methods, all right? It would be, you can't really break water down to simpler substances and have it be easy. All right, you can break water down with like electricity, but that's a one-way street. It's difficult to go back the other direction. Here are 4 substances, and I'd like you to try and tell me if you think they're elements, compounds, or maybe we just don't know because we don't have enough information. And remember, in science, it's okay to know that you don't know something. So the first one says it can't be broken down into simpler substances by chemical means. That's going to be the element, all right? You can't break elements down into other elements by chemical means. You're going to need some pretty hardcore kind of things. Substance B can't be broken down by physical means. Who knows? All right, that's really a hard one to know. It could be a compound, it could be an element. We need a little bit more information on that one. Substance C dissolves in water. Who knows? A lot of things dissolve in water. That's pollution and part of life too. So it's hard to know just based on that what it is. Could be a compound, probably a compound, but it could be an element too. Some elements are better at getting in water than other ones. Same thing with the next one. If you react with chlorine, and basically everything reacts with chlorine, it's hard to know. It could be an element, could be a compound, so many different things. So this problem is kind of silly on one level, but here's what I want you to pull away from it. In science, if you don't know, you say you don't know. All right, it's okay. And in these kind of problems, yeah, it's quite all right to say I don't know because we don't have enough information. That's a fundamental part of science, to say I don't know. Are these statements true or false? Compounds can be separated into their elements using chemical means. True. Certain kind of compounds can be broken down into their elements using just chemical means, and we'll see some of these examples as we go through, and that's kind of cool. Compounds can be broken down into the elements. Elements make up compounds. You can't break elements down. Second one, elements can be separated into their compounds. False. Sound effects not necessary. False, right, yeah. Compounds are made of elements. Elements are not made of compounds. Elements are the building blocks. The atom is the smallest one. So you bet you can break a compound down into an element, but you can't break elements into compounds. You would make the compounds from the elements. All right, C, a compound must contain at least two elements. True, all right? If you have CO, carbon monoxide, that's carbon and oxygen. Water is hydrogen and oxygen. Some elements can form what's called an allotrope. So for example, ozone is 3 oxygen atoms, and normal oxygen, as we're going to see, is only 2 oxygen atoms. Those are both versions of oxygen. I don't consider them to be compounds. Those are different forms of the element. Last one, a compound is a physical mixture of different elements. False. Compounds are chemical mixtures. There's bonding happening between the atoms. If they were just physical, you could use things like density and stuff in order to get them back, but that wouldn't work out. So yeah, compound is a chemical mixture, not a physical mixture. Number 19 is a way that starts to get you familiar with the periodic table. And the periodic table is a fantastic cheat sheet. There's all kinds of cool information on there, but you kind of got to know where the elements are on there. So I encourage you to have a periodic table next to you while you're doing anything in my class. And that includes exams and midterms and finals and all that kind of stuff. You got to go through and just kind of see where these different things are. So Li is the symbol for lithium, He is the symbol for helium, F is fluorine. There is an Fl, so don't call fluorine Fl. Zinc is Zn. Mercury's symbol is Hg. Chlorine is Cl. Gold is Au. And selenium is Se. Notice with the symbols of the elements, it's important that the first letter is capitalized and the second letter, if there is one, is lowercase. So like fluorine is just one big capital F, no letter after it. All right, no FLs, as I told you. On the other hand, things like chlorine, then capital C, small l. You'll never have to memorize the periodic table for me. You can always look it up on a periodic table. However, if you become familiar where like sodium is on the periodic table, it does make your life easier. Number 20 introduces some compound elements, which are very similar to each other. And sometimes these get confusing. So copper and cobalt. Notice how they both begin with CO. So I've had a lot of people put for copper CO, but that's not right. Copper is Cu and cobalt is Co. So remember that copper Cu, cobalt Co. Now, potassium is K and phosphorus is P. And man, do I see this one mixed up a lot. But just realize potassium comes from the Latin kalium, so it's different. And phosphorus, of course, is P. Iron and iodine get mixed up a lot as well. A lot of times people want to write down for iron, they want to write IR. But IR is not iron or iodine. Iron, thanks for playing. IR is iridium. So IR, iridium, is different than Fe, which is iron, and iodine is I, and they're all different. So just FYI. Finally, the last one, silicon is Si and silver is not Si. Silver is Ag, all right, it comes from a Latin term. Gold is Au and silver is Ag, so they are a little bit different. Just kind of be aware of these things as we go through. They'll become more familiar to you as you get through the course, but it's good to know. Okay, that's it for problem set number 1. I hope this video has been helpful to you and allowed you to see some of the parts of chemistry that we'll probably use the whole class. This is really the introductory kind of stuff. If you have further questions, definitely reach out to me. mike.russell@mhcc.edu is the best way. You can also talk to the LSC Avid Center on Mount Hood. Lots of people are there to help out. Okay, thanks for your hard work. Keep up the good work on your studying and have a wonderful day.